things we have walked behind last class? Behind
No.
complement?
No. Okay. So let's talk about RSA. I think this is lecture 13. RSA. RSA 1978, might want to know that. It's based on factoring large numbers, 200 digits or more. Okay. Best factoring algorithms are exponential. Remember we had P, NP, NP complete, and EXP. This is EXP, it's exponential. Okay. No known weaknesses. Not technically true. There is a hardware weakness, but still the algorithm wasn't the issue. It was an issue with the hardware. RSA is still used today. It is one of the most common ones used today. Okay. No known weaknesses. You choose large numbers, P and Q, large numbers, and you multiply. That becomes N. Okay, I'm going to walk through all this. Then you choose E, which I will give you. You're going to choose E, which is relatively prime to the totient of P minus 1 times Q minus 1. You're like, what? Think of it this way. N is P times Q. Can we get that? N is P times Q. That's all it is. The totient of N, which is this weird symbol that I finally got fixed today. It's been wrong forever. They finally got the right symbol in PowerPoint. The totient of N is P minus 1 times Q minus 1. So N is P times Q. The totient of N is P minus 1 times Q minus 1. Okay. They're not that different. Okay. If you can remember those two things, you pretty much got this licked. D. Yes, sir.
What is totient?
We're going to get there in a second. D. Don't worry about the formula for D. I'm going to show you how to calculate it. But it's approximately equal to E to the minus 1 mod totient of N. You're not going to do that. I'm going to show you how to do it in a second, okay? So to encrypt, we use an encryption key, and to decrypt, we use a decryption key. So it's E to the N, D to the N. That's all there is to it. And they're actually interchangeable. But whatever you encrypt with, you decrypt with the opposite. You can't, once you do it, you can't switch. But when you're creating the keys, you can decide this one's for encryption, this one's for decryption. You can't switch them after that point. Okay. So here's our encryption. We take our plain text, we encrypt it, mod N. That is our encryption, our ciphertext. Then the ciphertext raised to the D, mod N gives it back to a plain text. It's that simple. It is super duper easy. Okay, so all we've done, the only thing we have an issue with at this point is calculating D. So what the heck is a totient? Totient is also called Euler's totient function. It's defined as a number of positive integers less than or equal to n that are relatively prime. Says does not contain any factors in common with, or one is counted as being relatively prime to every number, or they are toatives. Okay? So there's 8 toatives to 24. 1, 5, 7, 11, 13, 17, 19, 23. So the totient of 24 would be 8. Do not do this on the test. It's not going to work. This is all theory. And okay, you got to remember, all this stuff we're doing on the test, these numbers are way too small to do this correctly. We really need huge numbers. Unless you want to be working with 200-digit numbers, just trust me. Don't, somebody last semester, well, that's the way you showed us. That's why I added. Do not, for the assignment, do not do this. Okay? Don't do that.
Wait, do not do this.
Do not calculate the totient of N by counting the numbers that are relatively prime to it. Don't do that. How do you get the totient of N? P minus 1 times Q minus 1. That's it. It's the only way. Don't count up the relative. I'm just telling you this, so if you happen to go look it up and find it, you'll realize what it is. Okay.
In this computer course, not a math course.
Exactly. Technically, you should already have these math courses to do these courses, but I'm not so worried about the theory. I'm worried about the application, like you said, computer course. Okay, the Euler's totient function is the number of positive integers. Okay, again, don't worry about doing it. This is how it works. So if N is P times Q, and P times Q are prime, then the totient of N is prime as well. Okay, but don't worry about that. Okay. I'm going to show you exactly what you need. It's very, very simple. There's just a lot of theory in here that you really don't really need to know. Okay, this is the algorithm. Don't write this slide down either. Okay, but if you're bored, you can go read all this stuff. But it just shows that it works. Okay, we're not going to cover the mathematical theory. Here's how we do it. This is exactly like the test question would be. Suppose I give you P is 3 and Q is 11. So N is P times Q. 33. Easy enough. Y'all with me?
Sure.
So the totient of N is P minus 1 times Q minus 1. So it's 2 times 10. You agree with that?
Yes.
So you got 20. So far, so good. Choose E is the 13. I will give you the 13.
Okay.
Okay? Which is relatively prime to 20, because that's to be relatively prime to the totient of N. If for some reason yours is not, just use the one I give you. Because again, the numbers are kind of just too low to make this really easy to do. Find D such that all that. We're going to show you how to do it in a second. D is 17, okay? I will show you how to get D. We haven't got there yet. Okay? Our public key would be E to the N. That's what we're going to encrypt with. So E would be 13. Again, I gave you E right up here. Okay? E and N, I gave you N right here. So you know where E and N came from. The only thing you're missing is this whole 17. You agree? You got everything else, correct? So where everything else came from. So if I give you the plain text, you go 7 to the 13 mod 33 gives us 13. 13 raised to the 17 mod 33 gives us 7. So it works perfectly. So you should be able to do everything except for the D at this point. Correct?
Yeah.
Okay, just making sure. How to calculate D? You use modular inversion, but no, do not look it up and try to do it that way. I'm going to show you an easier way to do it. Okay? You use the extended Euclidean algorithm. Much easier way to do it. Okay. Good, we're going to get there. Just hold on. Suspense is killing you, I know. So when using RSA, choose prime numbers. They're normally 100-digit numbers. If you want to do it like in Java, you have to use, instead of an integer, you use big int, because that can handle large numbers. Calculate N, we know what that is. Okay. So we want 200 digits or so for larger numbers. Then choose E, which again, in this case, I give it to you. Normally you would just pick one. Compute D, which we're going to see how to do that. Then you have your keys. Then once you have your P, your E and D, you can literally throw away P, Q, and N. You no longer need them. They're only needed to calculate N and D. Okay? So what the heck is congruent? Because over here, if you notice, I say calculate D such that E times D is approximately equal to N mod, or 1 modulus totient of N. Okay? In other words, it's congruent. And I put this definition in here. Coinciding exactly when superimposed, like congruent triangles, or of or relating to two numbers that have the same remainder when divided by a third number. For example, 11 and 26 are congruent when modulus is 5, because they end up with the same result. Okay? Not critical. I'm just showing you some of the stuff that's important. Now, here's the test question. Assume P is 3, Q is 11. This is exactly what the test question will look like.
Okay.
So, you know, I mean, this isn't the question, but this is what it'll look like. Assume P is 3, Q is 11 for the RSA crypto system. If the public key coefficient E is 13, compute the coefficient D. Well, we have P and Q, so we can calculate N. We get 33. We can calculate the totient of N, which is 20. I give you E, so we need to come up with something. So E times something mod totient of N will approximately equal 1. So what is that? This is so easy.
So
Look familiar? Remember I had y'all do that comparison thing? Here's why.
Next comparison.
I'm going to use it.
A lot longer.
Well, this is just because D in this case happens to be 17. But in this case, you use the totient of N and E. That's it. If you could do the comparison method, you got it.
That's it, man. That's all we have to do.
Isn't that easy?
time consuming.
Just make, again, that's just because D's big on this one. Just remember, you always have to start with 1, 0, 0, and you keep going until they match, and then you use the number here. Do not give me 11. 11 is not the answer. There's always somebody who gives me the 11. Not the answer. So remember, Totient and E, 1, 0, 0. Then 20 plus 1, plus 20, plus 20, plus 20. Keep going. 13 plus 0, and plus 13, plus 13, plus 13. Then you just compare them. When they match, boom, 17 done. That's all there is to it. That's how you do D. Isn't that much easier than all that math?
Yes. Yes.
See, and you wonder why I made you do the comparison method. Okay. So in summary, we know what N is. P times Q. We got that. Totient of N is P minus 1 times Q. Someone's cooking dinner. Smells good. So totient of N is P minus 1 times Q minus 1. You tell I'm hungry?
Yes.
I'm going to give you E. Okay? We know what D is now. Super easy to do. Then you take P to the E mod N, and then C to the D mod N. That's it. We're done. You must admit, that is probably the easiest encryption algorithm we've... Okay, Caesar cipher was easier. But not much. Could you every step in here? Think you can memorize them?
Yeah, we're ready.
Compared to knapsack, this is like what? Step 0.1? Knapsack's got what, 40 steps? This is like you ain't even got nothing. All right, there you go.
Yeah, okay.
Oh, that's all right.
That's
it.